Welcome to the overview of counting and cardinality as it aligns to the Common Core state standards and the Common Core essential elements. Counting and cardinality enables students to use numbers, including the written number, to represent quantities and to solve quantitative problems, such as being able to count objects in a set, counting out a given number of objects, comparing sets or numerals, and modeling simple, joining, and separate situations with sets of objects. This will eventually lead to solving equations, such as 5 plus 2 equals 7, and 7 minus 2 equals 5. Students can choose, combine, and apply effective strategies for answering quantitative questions, including being able to quickly recognize the number in a set or counting to produce a set number of objects. In order to achieve all these objectives, the domain of counting and cardinality has three primary goals. 1. That students know number names and the count sequence. 2. That they can count to tell the number of objects in a set. 3. And that they have the ability to compare numbers. Let's take a moment and look more deeply at each one of these particular goals. Houston, Richards, and Breyer in 1982 stated that learning the order sequence of counting words up to 20 is essential. However, it is a serial recall task. The words in the sequence must be recalled, and they must be produced in the correct order. The acquisition of the sequence from 20 to 100 is also a serial recall task. However, it is one with a repeating pattern. Following the acquisition of this skill, each word in the sequence can serve as a stimulus for the recall of the next word. Several years are often required for the acquisition of the sequence of number words. To count to tell the number of objects, students should understand the relationship between number and quantities and connect counting to cardinality, or the final number in the set. When counting objects, students should say the number names in the standard order, pairing each object with one and only one number name, and each number name with one and only one object. They should understand that the last number name said tells the total number of objects contained within that set. They should understand that each successive number name refers to a quantity that is one larger than the previous number, and they should also count to answer how many. For as many as 20 things arranged in a line, or a rectangular array, given a number 1 to 20, students should be able to count out that many objects. In order to compare numbers, students should be able to identify whether the number of objects in one group is greater than, less than, or equal to the number of objects in another group by using the matching strategy or the counting strategy. These standards follow successful international models and recommendations from the National Research Council's Early Math Panel report by focusing early work on learning how numbers correspond to quantities and learning how to put numbers together and take them apart, the beginnings of addition and subtraction. The primary intent of the counting and cardinality standards is to build what researchers often call number sense. In 1954, Tobias Danzing introduced the term number sense. He described it as a person's ability to recognize that something has changed in a small collective when an object has been added or removed from the collection without the person's knowledge. We have number sense because numbers have meaning to us, just like words or music, and we're able to acquire the ability to recognize a change in sets or the size of objects at a very young age and without a tremendous amount of effort. Keith Delvin redefined the definition by suggesting that number sense consisted of two important components: the ability to compare the size of two collections shown simultaneously, and the ability to remember number and objects presented successively in time. Just because we're born with number sense does not mean we can become great mathematicians, but it does mean most of us have the potential to be a lot better at arithmetic and mathematics than we originally had thought. A key tool in developing this number sense is the use of a number line. In order to use the number line, we need to understand two basic things. The first one being quantity, which is the physical amount of something, and the second one being magnitude, the amount or quantity in relation to other quantities. It is important for students to associate magnitude to the number line, or more specifically, the idea that moving in a certain direction implies an increase in quantity. What Sharon Griffin and others found in their work with young students was that students must understand quantity in the earliest form of a number line in order to do simple tasks such as counting independently. This involves two developmental leaps. The first leap in mathematical development is connecting these two concepts by being able to solve problems of quantity through an early understanding of the number line via counting. The second developmental leap occurs when students are able to connect understandings of quantity in a number line with a symbolic representation. Griffin found in her research that students who were behind in math in the third grade did not have an internalized sense of the number line. Griffin's research suggests that students must understand not just the traditional number line, but different forms of the number line. We see here that there are two multiple number line representations, referred to as lands by Griffin. In object land, students count and compare sets of objects or pictures. Which is bigger, which is smaller, and how many do you have are questions that are often associated with this land. In picture land, number is represented as a set of patterns, such as on a die or tally marks. Questions often associated with this particular land include what did you roll, which is more, or which is less. In line land, number is represented by a position on a path or on a line. We may ask questions such as what is your position on the line, where are you now, how far did you go, and did you go forwards or backwards. In Skyland, number is represented as a position on a vertical scale, which is a thermometer or a bar graph. We may ask students how high are you, how low are you now, and what number or amount is higher or lower. Finally, in Circle Land, number is represented as a point on a dial, which is a clock or a sundial. Typical questions include how many times do you go around the dial, which number is farther, or which number is less far around. Let's examine how our brain works, and later we'll discuss how this knowledge changes our instruction. In 1992, Karen Wynn found that very young children could add. She performed an experiment where an object was placed in a case, a screen was raised, and a second object was added. When the screen dropped, if the possible outcome revealed two objects in the case, the children did not seem surprised. However, if the screen dropped revealing only one object or an impossible outcome, these young children seemed surprised and stared at the objects. The same thing is true for subtraction. This was observed when there were two objects in a case and a screen came up and a hand came in and removed an object. If the screen dropped and there was one object left in the case, the children were not surprised. However, if the impossible happened and two objects were still in the case, the children were surprised. Young children can also reliably see small quantities, but not larger quantities. Just like adults, young children can see very small quantities. By the age 4 or 5, we are able to see 4 or 5 objects collectively as a set and understand the number that is contained within that set. But for larger quantities, we still need to be able to organize these into smaller sets that typically consist of 5 or fewer. That's why we need to gather other resources to help us make sense of a number, such as the numeral. We teach digitally, but we have analog brains. We still process quantity in an analog fashion, even though we have developed a digital system to help us deal with larger numbers. Although young children see small numbers, they have a difficult time understanding the numerical representations 1, 2, and 3. This is particularly evident when we talk about 3 being bigger than 2, or 2 being bigger than 1, when the written numerals appear to be the same size. However, in the analog model, we can see how 2 has 2 ones within it, and that 3 has the quantity of 2 and another one within it. Research is extremely clear that it takes much longer to decide on the larger of two numbers that are a small distance apart than to decide on the larger of two numbers that are a greater distance apart. It's obviously easier for us to understand that 3 is bigger than 1. And we can do that much more quickly than if we were trying to decide if 2 is bigger than 3. The same is true here. We are able to identify that 15 is smaller than 25, much more quickly than if we were looking at 15 as compared to 18. The speed at which we compare two numbers obviously depends on the distance between them. It takes far longer to decide that 6 is bigger than 5 than to decide that 2 is larger than 1. For numbers of equal distance apart, larger numbers are more difficult to compare than smaller ones. Let's examine some basic ideas around counting. The first idea is the hierarchical inclusion of numbers. As the model depicts, we can see how the quantity of 4 holds within it the quantities of 3, 2, and 1, just as the quantity of 5 holds within it the quantities of 4, 3, 2, and 1. There is also the idea of the ordinal or sequencing property. The vertical number line is an important way to show our students that the numbers are getting larger or bigger as we move upward on the number line. This is also a great way to allow children with visual impairments to have an opportunity to grasp the idea of how the quantity of 3 is made up of 2 and 1, more when using physical manipulatives. Gelman and Gallistel's counting principles provide us with an understanding of the skills that students need in order to count. The first one is 1-1 correspondence, that each item counted gets one number tag. The second is stable order, which means that numbers always stay in the same order, 1, 2, 3, 4, 5, and so on. The third principle is cardinality, that tells me that the last item's number represents the total number in the entire set. Abstraction enables students to understand that objects are not necessarily needed when we count. We can count what we cannot see. Finally, order irrelevance tells me that objects can be counted in any order as long as there are other principles in place. Therefore, I could start on the right of a set and count to the left, or I could start on the left and count to the right, or I could start in the middle and count out as long as each item in the set has one count. Students who struggle with counting commonly think that certain features are essential for counting. One is a standard direction, that counting must proceed from left to right. These students may also believe that objects must be adjacent or placed next to each other in order to count them. They may also think that objects must be pointed at each other in order to count them, and that one must start at the end of an array to count. Students who struggle with counting do not understand that you could start counting in the middle and count outward as long as each item was counted. One way we are able to understand what children should be able to do is through the research around learning trajectories. Learning trajectories are learning progressions. These trajectories to identify waypoints along the path in which a student's knowledge and skills are likely to grow and develop. We can use this information as an empirical basis for choices around when to teach which skill to each of our students. Learning trajectories help us understand the skills that we need to acquire and the order in which we need to acquire them. For the typical student, we often associate particular ages with particular skills. For the group of students we often work with, these skills may not come at the expected age, but the sequence should be applied to all students. When we discuss counting and cardinality, it's important for us to understand that there are several progressions that originate in knowing number names and the count sequence. Once we understand the counting sequence, it is important that we become familiar with counting on from any given number. Skip counting by 2, 5, 10, etc., and even counting backwards. Let's watch two videos in which students are learning to count backwards. Here we will see a child using technology and the number line paired with backward chaining instruction to master the skill of backward counting. It's interesting to watch the first time the student tries it because he is not referencing the numbers correctly, e.g. saying 7 and pointing to the number 6 until he gets to 5. At this point, we start to see him really understand the skills at hand.
9, 8, 7, 6, 5, 5, 4, 3, 2, 1. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Oh, you want to eat our brains for dinner?
You did it!
Oof.
Here we will see a child practicing the same skill but without the aid of manipulatives. We can once again see the exact moment when the student truly understands the sequence/skill that he is trying to achieve.
Yeah.
Okay. 7.
5. Good.
That's okay, you forgot. Okay, forgot. 7.
Very.
I get my pony book.
Oh, Pete.
6.
Okay.
5.
5. You can do it.
4. 3. 2.
Recognizing the number of objects in a small set or in a small collection is part of that inborn number sense that we discussed earlier. It requires no counting because as long as the child can see the set of objects, the numerosity is identified in an instant. Researchers often call this subitizing, from the Latin word subitus. But when the number in a collection exceeds the limit of subitizing, often 5 or 6, counting becomes necessary. Clements, in 1999, described two types of subitizing, perceptual and conceptual. Perceptual subitizing involves the ability to recognize a number without using other mathematical processes, just as you do here when you recognize this number as 4. However, when we display a greater number of dots, you must employ what he calls conceptual subitizing. Conceptual subitizing allows one to know the number of a collection by recognizing a familiar pattern, such as 4 and 3, or 3, 3, and 1. Creating and using conceptual subitizing patterns helps young children develop the abstract number and arithmetic strategies they will need to master counting later on, such as the ability to see 7 as 3 and 4. Here's a video of a teacher using the idea of subitizing to begin to instruct her class. As with anything we teach, you will notice that subitizing is easier for some students than others at this point in time.
Okay, today we're going to do our subitizing, and we're going to do it with the dice. Now we'll also do it with our hands. Is that cool? Y'all ready? Okay, you ready? Okay, do it 3 times with the dice, then we'll do it 3 times with our hands. Ready? Okay. William.
4.
Awesome. Kelly.
That's the same number as Lou.
And what number was that?
F-O. 4.
4. Good job. Excellent. F-O-U-R. There you go. Okay. Whoop. What was that? Jacques? No, you got to take your hands off your eyeglasses. You ready?
Yeah.
Okay, look so you can see it. You ready?
2.
Good job. Are you ready, Zach?
1.
Good job. Okay, ready, Lexi?
3.
Zach, it's you.
5.
You said it before I even got the screen up. Good job, bud. Man, you guys are good. I can't trick anybody. Okay, let me see.
Miss
Let
J.
me see if I can get
Noah.
oh, see if I can get it. Oh,
3.
oh, didn't even full hand that time. Okay, let me do.
Okay. Go.
What was it?
2.
Man, you're good, Kelly.
Because I closed my eyes by magic.
Number sense provides students with a limited ability to subitize and determine the number of a small group of objects. As the number of objects increases, the brain has to resort to a more exact system of enumeration. This is what we often call counting. At the same time, skills necessary to do exact addition and subtraction begin to emerge. How does all this research apply to our classrooms? We can use things such as tens frames to help students explore how our base 10 system works. If we think of the number 12, using tens frames, students can see that this is one full set of tens and 2 ones. This later leads to the understanding of addition, whereas if we had given students a problem such as 8 plus 5, they could understand that 8 consists of 5 and 3 more, which is 2 away from a full set of 10. They then can understand that they can decompose the 5 to 2 with 3 left over. They can combine the 8 and the 2 from the 5, and they end up with one set of 10 and 3 left over for a total of 13, or 1 10 and 3 ones. By asking students to think in tens frames, we encourage them to not only start to understand true quantity, but we lead them to the understanding of our base 10 system. Ideas to help us develop number sense in our classrooms include pairing numbers with meaningful objects, using language in the correct way, using counting activities that relate to the student, connecting the counting to the environment, providing experiences for students to explore and participate in using number lines, and planning meaningful estimation experiences. One such activity may include students being given the scenario of Ben and his bunnies. In this story problem, Ben has 10 bunnies in his collection. He plays with them often and keeps them on 2 shelves in his toy room. How many different ways can he arrange his 10 bunnies on these shelves? Giving students the manipulatives along with 2 shelves can help them formulate all the different combinations of 10, such as 2 bunnies on the first shelf and 8 bunnies on the second shelf. Due to the fact that no additional bunnies came and no bunnies left, even though they are in different arrangement, there are still 10 bunnies in Ben's collection. Let's take a moment and meet Stephanie. Stephanie is the student in the video. The teachers are trying to encourage her to count using numbers written on a large piece of paper.
1. Set. 2. 2. Let's count. 1, 2, and 3, Stephanie. 1, 2, 3. Good job.
Here we see Stephanie counting bears. When the teacher moves from bears to clapping, we see that Stephanie becomes a little more engaged. She starts clapping her own hands. Clapping is more relevant for Stephanie when learning about counting than counting bears or written numbers.
Can you help me count, Stephanie? 1, 2, 3. Can you hear the bears? 1, 2, 3. Here, let's see if we can clap our hands to 3, Stephanie. Listen. 1, 2, 3. Does Stephanie want to help? 1, 2, 3.
Eventually, the teacher makes a connection to something very real in Stephanie's environment, her rocking chair. Stephanie begins to understand counting because it's connected to her own experience. Let's watch as we see her begin to understand 1, 2, and 3.
1, 2, 3, and stop. Your turn, Stephanie. Rock 3 times. Can you rock 1 time, Stephanie? Show me 1 rock. That's 1. Can you rock 2 times, Stephanie? 1, 2, and stop. Can you rock 3 times, Stephanie? 1, 2, 3, and stop. Are you ready to count with me? Can you help me count? Say 1, 2, 3, and stop. Good job.
We can see how these ideas around developing number sense enabled the teacher to be much more successful in helping Stephanie understand the counting sequence. Counting and cardinality focus heavily on the development of the number sense. Resnick and his research partners state that strong indicators of number sense include a child's ability to decompose, taking a larger number and splitting it up into 2 smaller numbers, which is the beginning stage of subtraction. Another indicator of number sense is the child's ability to recompose, meaning putting smaller parts together to form a larger number, which is the beginning of addition, or simple calculations. Having a child use what they know to derive what they don't know, the ability of a child to use flexible and multiple representations of a number, and a desire to make sense of numbers all fall under the development of number sense. Thank you for taking the time to complete this module on counting and cardinality.